So we're going to go ahead and look at the different types of solids and basically look at their characterizing features and look at ways to differentiate between the different types of solids that are possible for different types of materials. Okay, so there's two major types of solids. There are amorphous solids and crystalline solids. So amorphous solids basically have a fair degree of disorder to their structure, or basically some inconsistency. This is not normally how we see the structure of solids coming together in nature. However, things like glass and plastics are representations of amorphous solids. So basically, what you'll end up with is a substance that has a degree of order. There's going to be, some repeating units. However, there are going to be irregularities in that structure, and this leads to certain features, like instead of having a specific melting point, the melting point of amorphous solids will typically occur in a range. So between this temperature and this temperature. The other type of solid that's more common is the crystalline solid. And basically, in the crystalline solid, there's a regular arrangement of crystals. All of the molecules or atoms or ions that make up that structure occur in repeating pattern and are very structured. So in this crystalline type solid, the melting point range, the melting point is no longer a range but a specific point. And that's in obviously stark contrast to the range that we anticipate up here with the amorphous solids. So amorphous solids, they have some order, but there is disorder to the structure, and they're not very common. Crystalline solids have a very specific arrangement of the components that make up its structure, and basically melting point in these types of structures has a very specific value versus the range that we see with the amorphous solids. So different types of crystalline solids that we're going to be looking at today. So the four that we're going to be looking at are ionic solids, which are characterized by electrostatic interactions between ions. We're going to be looking at metallic solids, which are represented by a sea of electrons. We're going to look at covalent network solids, which basically are represented by atoms that are covalently bonded across an array. Okay, and we're going to look at molecular solids, which are formed through the intermolecular forces between atoms. So ionic solids are held together by the electrostatic attractions of cations and anions. Okay, so we know that if we have a positively charged cation and a negatively charged anion, that there are going to be attractive forces between these two ions. Okay, and we've already looked at this. We've already studied ionic solids. Basically, they orient themselves to where the positives and negatives can be in close proximity. They attract one another and basically build on each other and form, large lattices or large three-dimensional structures of those specific ions. Okay, and we also looked at the lattice energy being affected by the charge and size of the ions, right? So the larger the charge, or that Q value, if you remember, and the smaller the size, the D value that we looked at several chapters ago, basically leads to stronger attractions and subsequently higher lattice energies. Okay, so we know our ionic solids because they have this basically repeating setup and overall additive attractive force between the various sodium chloride ions. They have really high melting points, so lots of energy has to be put into the solid in order to break up the lattice energy, or in order to break up the lattice. Okay, ionic solids are insulators. They don't conduct electricity very well. The electrons have been transferred between the ions, or between the atoms to form ions. So those electrons are kind of wanting to stay put in their current locations. They're also very brittle. Okay, and the reason why they are brittle is because of the arrangement. Okay, so as we see here, okay, notice there's a very specific repeating pattern. You got blue, green, blue, green, blue, green. And then across this direction, we have that blue, green, blue, green, blue, green. Now, if I were to apply a shear force onto one of these rows and basically cause all of these atoms to shift down, okay, one position, what would end up happening is I would have, a green green, okay, and then maybe a purple purple, okay, and then green green interacting. So basically what I'd end up doing is putting ions with the same charges into close proximity. And we know that this will lead to repulsive forces and subsequently cause the breakdown of the lattice structure. Okay, so the fact that they are brittle is caused by the fact that any alteration to the repeating units causes repulsive forces. So metallic solids basically are characterized by the electron C model. We could also look at it with respect to molecular orbital theory, but that's outside of the focus of this class. So the electron C model basically just says that we have metal ions, okay, that are basically free floating within a sea of delocalized electrons. So delocalized means that the electrons are not in a specific area. They move randomly throughout this structure. Okay, so and these free-floating or delocalized electrons contribute to a lot of the features associated with metallic solids. Okay, the ability to conduct electricity and heat. So the electrons, when we apply electrical current, basically the electrons don't have a problem moving on through the metal because basically the electrons are just floating randomly anyway. Heat works in that same way. Basically, these delocalized electrons allow that heat energy to be transferred through in a very easy way. Okay, the malleability and ductile features of metals, their ability to be shaped or drawn into wires, is also basically predicated on the idea that the electron C model allows the electrons to just reorient themselves. Okay, so if we, hammer on the metal or pull on it, basically the metal ions and electrons are just going to reorient themselves and still stay connected, but basically get drawn into whatever shape we desire. So molecular solids form when basically the intermolecular interactions between molecules cause solidification. So basically the intermolecular forces, so those London dispersion forces, okay, the dipole-dipole forces we've discussed, the H bonding, okay, and the ion dipole that we've all discussed are going to also affect the formation of these molecular solids. So now we know that intermolecular forces are weaker than other types of interactions that can be found in both solids and liquids, but because of that, we know that the melting point in that solid is going to be lower, much in the way that the boiling point of a liquid is going to be lower if the intermolecular forces are weaker. So they correlate in that way pretty directly to the liquid features that we saw when we discussed intermolecular forces. So basically, the types of molecules that you have in the molecular solid are what are going to determine what types of interactions you have. Okay, so something that's nonpolar is going to have those London dispersion forces, something that's polar, that dipole-dipole situation, okay, and so on. Okay, another thing to consider is that the shape of the molecules is also going to affect the intermolecular forces, much like we saw with the liquids. So, a molecule that has a very large structure or interferes with the basically proximity of the molecules are going to negatively affect the ability of the molecular solid to be able to form. So that will subsequently affect stuff like your melting point. So if we look at, examples here, okay, that we have down here, we have phenol, we have toluene, and we have benzene. And if we go ahead and look at their relative melting points, the phenol over here has the highest of the three, okay, while benzene and toluene are on the lower end. And if we look at how melting point is affected, okay, basically both shape and intermolecular forces are going to have a say on that. So if we look at the case of benzene versus toluene, okay, they're going to have similar intermolecular forces, and the intermolecular forces that are present are going to be altered by the presence of this CH3 group in the toluene. So where benzene is nice and planar and the molecules can stack on top of each other and be in close proximity, this CH3 or this alkyl group that's there basically it disrupts that planar aspect of the molecule and makes it where the toluenes can't get as close to one another, and subsequently affects their ability to interact. So the intermolecular forces are going to be less strong in the toluene example, and we see this with the melting point issue as discussed earlier. Okay. Okay, now if we look at the phenol, on the other hand, it also has a branch on its benzene ring, okay, but in this case it's a hydroxide or an OH, and as we know, OH is capable of doing hydrogen bonding, so that confers a stronger intermolecular force compared to the others that are present here, and you subsequently end up with a slightly higher, or actually rather significantly higher melting point. So remember, your type of intermolecular interactions are going to be important, as well as the shape of the molecules are really going to dictate the features associated with melting point and stuff like that in the molecular solid. So the newest of the group, I think, that we have not really spoken about before today at all, are the covalent network solids. And these are kind of unique in that they are solids that are held together by covalent bonds that are repeating throughout a three-dimensional structure. Okay, so I'm not just talking about, a carbon, hydrogen, hydrogen. I'm not talking about just that type of covalent bond. What I'm talking about is a covalent bond that ends up repeating itself. Okay, so if we look at diamond, okay, diamond is basically just carbon, okay, and what happens in diamond is you have tetrahedrally oriented carbon atoms, okay, so that's what I'm representing here, that tetrahedral shape, and basically all of these carbons are then bound to other tetrahedrally oriented carbons, and those carbons are bound to other ones, and so on and so forth, and basically you get this huge array of covalently bonded atoms. Okay, and it leads to the really high melting points and the hardness associated with covalent network solids. So this is in stark contrast to molecular solids, because in molecular solids all you have is basically intermolecular forces that are holding molecules together. So the most common examples of covalent network solids are diamond and graphite, and basically they're allotropes of each other, so meaning that they're made of the same substance, they're in the same state of matter, so they're both made of carbon, they're both solids, however they're connected differently, and that leads to different features. Okay, so as I said, this diamond orientation is tetrahedrally oriented, they're all bound to each other in this repeating array. In contrast, basically, the graphite is organized in sheets, and they are also bound in an array. As you can see, these carbon-carbon bonds basically repeat and interconnect in these sheets. However, they form these sheets, and then these sheets interact by intermolecular forces and create the graphite allotrope. So basically what we see here are two different substances that are both covalent network solids, but depending on the type of orientation and connectivity, you have very different features. We know diamond is the hardest substance, while graphite, which is present in your pencil, is obviously very easily able to be sloughed off and broken. And it's also one of the reasons why we use graphite as lubricants. So basically, there's specific substances that are going to form these covalent network solids. Obviously, carbon compounds that can repeatedly bond, those are options. Other options are silicon, germanium, okay, quartz, so silicon dioxide is a great example, silicon carbide, okay, boron nitride. These are all examples of covalent network solids. So they're going to orient in a way in which the silicon and carbon, or the boron and nitrogen, or the silicon and oxygen are basically connected by these covalently bonded network solids array. So high melting points, hardness, these are things that are associated with covalent network solids, and basically they're a very unique substance. So let's go ahead and let's identify basically the type of solid that we have, or what kind of solid will be formed from the various compounds or atoms seen here. Okay, so in this first situation we have sodium chloride, so NaCl. We know that this is an ionic compound. Okay, so it's going to be an ionic solid. It's pretty straightforward. Okay, all right, HCl has a covalent bond, okay, between it. However, hydrogen is not going to go on and bond to other atoms covalently, right? It can only form a single covalent bond, so we know for sure that this is going to be a molecular solid. And molecular solids form from intermolecular forces, and the types of intermolecular forces that are causing the formation of this molecular solid are the dipole-dipole interactions that occur because that's a polar molecule. Okay, Cl2, okay, it is a molecule with covalent bonds. It's not carbon, it's not silicon, it's not germanium, it's not some of the ones that we talked about in terms of the covalent network solids. So we know that this is just going to form a molecular solid. Okay, and the intermolecular forces that are going to cause the formation of the molecular solid here are the London dispersion forces. Okay, here we have an atom of zinc. Okay, so if we have this in a repeating array of solids, okay, it's going to be metallic. The reason why I know it's metallic is because zinc is a metal. So that's the kind of bonding or kind of solid that will be created. Okay, and if we come down here, we have an individual element. We have silicon. Okay, silicon's one of the atoms that we know, or the types of atoms that are involved potentially in covalent network solids. So we're going to indicate that this is a covalent network solid. Okay, and basically this is how you'd be identifying each of your substances. Okay, we do want to know and be able to identify, features associated with these different substances. So, ionic solids, they occur in lattices. They have, high melting points. They're brittle. Okay, why are those the case? We should think those through. Molecular solids typically have low boiling points, low melting points. And basically we can look at these and compare molecular solids. I could ask you, which one of these is more likely to melt at a lower temperature. Okay, and of course you're going to say the Cl2, and the reason why is because in order to break up the molecular solid, you need to break up the London dispersion forces. Okay, and that's a weaker force, or that's a weaker intermolecular force than the dipole-dipole interactions. So you would subsequently say that that's the case. Okay, metallic solids, they're represented by a sea of electrons. We know that they're malleable, they're able to conduct electricity. These are all features you would anticipate. And then covalent network solids, okay, obviously they're going to be really hard for the most part, at least relative to other covalent compounds, which, a lot of times are liquids or softer solids. Okay, and, basically they differ drastically when compared to other covalently bonded molecules. So these are just some things to think about when we're looking at solids. Make sure that you're comfortable with each definition and the details associated with each.